Welcome back to Applied Algebra and Trigonometry. Today we're going to be talking about the law of cosines. From our discussions in the previous lesson, you should remember that there are four combinations, or four types of triangles, that you need to recognize if you're going to solve an oblique triangle. You may have two angles and one side, which could be angle, side as you go around the triangle, or it could be angle, side, angle as you go around the triangle. You could also have two sides and an angle opposite one of them, which could look like any of these examples. And please remember that you may not see them in that orientation, but at any time you can turn the page around, you can redraw the triangle to make it easier to work with for you. Also, please remember that there are two possibilities if the side opposite the angle is shorter than the side that is adjacent to the angle. So that's why you always have to be careful when you have angle, side, side. You cannot prove congruence with it, but you may apply the law of sines as long as you watch out for that instance. With both of these combinations of angles and sides, you can use the law of sines. However, there are two more combinations of sides and angles that you may encounter for which you cannot use the law of sines. The third combination you may see is two sides and the included angle, or side, angle, side. And the fourth combination you may see is three sides. So if you know two sides and the included angle, or three sides of a triangle, you can also solve for everything else you're missing. You cannot use the law of sines, however. You must use, instead, the law of cosines. Remember good old Pythagoras and his formula that we can use to calculate a side of a right triangle? Well, the formula that represents the law of cosines looks very similar. Once again, I'm reverting to the cursive small c to differentiate it from my capital C. And the law of cosine states that side c squared equals side a squared plus side b squared. Looks the same so far. But then you have to subtract 2 times side a times side b times the cosine of angle c. Your textbook provides a derivation of that formula. Therefore, I'm not going to do that for you right now. So let's look at an example. Here's the first example where side A equals 87.3. I'm not giving you units for that. Imagine it's inches or feet or whatever. Side B is equal to 34.0 units. And notice that is angle C. It's a capital C equals 130.0 degrees. All right, while we're here, let's just notice that there are 3 significant digits here, 3 here, and 4 here. Let's say I'm being asked to solve the triangle, so I have started my chart. Now I know what I need to find. I need to find side C, angle A, and angle B to completely solve this triangle. As I look at those measurements, though, it looks like I need to redraw my triangle. I need a large angle C, an angle A that equals 87.3, and an angle B that equals 34.0, and then we have side C, which is what we're looking for. So looking at the general form of the law of cosines, what parts do I have for this problem? Let's see, I have side A, I have side B, and I have angle C. Oh, and I have that side A, that side B, because it's the same thing. I do not have this side C. So since it's already set up just like this, let's try to find side C. Before we start plugging numbers in, let's manipulate this formula just a little bit. Because if this is true, then if we take the square root of each side, the entire side, this is what we have to do to solve for side C. Now let's plug everything in. As always, I suggest you put parentheses where all of the variables go, and then go back and fill them in. So A is 87.3, B is 34.0. A shows up again in the formula. 2 times A times B times the cosine of c. Please remember that's minus 2 times a times b times the cosine of c. As you're using your TI-89, please remember at the end that after you type in 130.0, you have to close the parenthesis for the cosine, but then you also have to close the parenthesis for the square root. This should give you c equals, which rounds to 112 for when we are reporting it in our chart. Now, when you're working with this, to avoid rounding error, you can scroll up to this number when you need to input it into a new formula and hit enter, and it will send the unrounded form into the equation with which you're working at the time. For instance, when we are solving for the next part of our triangle. All right, we found the big side C, the big side C, the longest side. Now we need to find angle A and angle B. So, are you ready to go through the law of cosines again? I'm not. I want you to notice something. Without this side C, which we just found, we do not have a pair of an angle and its opposite side, so we cannot use the law of sines. But as soon as we found that side C, we now have a side and its opposite angle. So we can revert to the law of sines to solve the rest of this triangle, which is a much easier proposition. There is my first ratio composed of side C over the sine of angle C. Wait a minute. Let's not forget an important lesson we learned from the law of sines, and that's about ambiguous cases. Be careful. If you have the case side, angle, side, and you do not have an obtuse angle as your starting point, start out just fine, and we can use the law of sines to find the measure of side C, and that turns out to be 39.7. So we can now set up a ratio, 39.7 over the sine of 35 degrees. Okay, and if we're searching for angle B next, just because, we'll wind up with doing this, taking cross multiplying, taking inverse sine. We'll wind up with B equals 75.5 degrees, which looks pretty good, and then we can just subtract to find angle A. But take a closer look at my diagram. Because I have actually drawn it fairly accurately, doesn't it look like angle B here is slightly more than 90 degrees and not 15 degrees less almost? Your calculator is giving you this solution. You found an ambiguous case. Your calculator is giving you the acute angle, and then you'd have to work to get this obtuse angle. But you might miss it doing it that way. If instead you are given an acute angle, when you are ready to calculate one of the other angles, make sure you use the one that is most acute of those remaining. In other words, which one of these angles, A or B, has the smallest opposite side? The answer is clearly A, so A is the smallest angle of those remaining. Therefore, that is the one for which we should solve. Solving for that, we would set it up as 45.0 over the sine of A, and when you solve for it this way, what you get is A equals 40.6 degrees. If you then take 180 degrees minus 35 degrees, which you were given, and subtract from that the 40.6 degrees that you have found, your final answer for the remaining angle B will be 104.4 degrees, which is a far cry from our original 75.5, and it tells me that my triangle could have been drawn better. So if you are given the measurements of two sides and the included angle, side angle side, with an acute angle between the two sides, find the remaining side with the law of cosines, and then find the smallest remaining angle with the law of sines. Then you can just do subtraction to find the third angle. So let's get back to the original problem though. Here I am given an obtuse angle, the obtuse angle of the triangle. You'll never have two in the same triangle. Then I can solve for either angle A or angle B. I'm going to go for A because it's on top. 87.3 of my chart, on top of my chart. And so side A goes on top of my ratio. And below I have the sine of angle A. Cross multiply and solve. Be careful with your parentheses when you enter it into your calculator. And remember to scroll back up into the history of your calculator to grab 112.21914 blah 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 to avoid rounding error. Hit enter and finish your parentheses and you should get 36.6 degrees. So that's angle A. Now the only thing we have left is angle B. Shall we go back and do law of cosines or law of sines? No. Let's do instead 180 degrees. And remember that is a perfect number. It's an exact number actually. We're going to subtract from that 130.0 degrees, and we're going to subtract also 36.6 degrees to get 13.4 degrees. Yay. Now we are done. 13.4 degrees. Now that took a while. It will get a little bit faster as you work through it and become familiar with it, and you won't have me slowing down and explaining everything as you go. Please do not get hung up about the order of the letters, but rather notice the relationships among the letters. For instance, this side C is opposite the angle that shows up here. So the side on the left is opposite the angle that is in the formula. Okay, then the other two sides come into those positions. If you are looking for side A, or if you are looking for angle A, you could put them in this position. That would leave B squared plus C squared as the two remaining sides, and that would mean the rest of the formula would be 2 times B times C cosine of A. Likewise, if you're looking for side B or angle B, you could use this formula where you have A squared plus C squared minus 2. The A comes here, the C comes here again, and then you have the cosine of B. So it's the relationship amongst the various positions in the formula that you need to notice. What does all this have to do with vectors? Let's imagine this situation. You have a 175-pound weight supported by two cables. Each cable will be pulling upwards at an angle in this direction and this direction. Okay, in other words, those cables have to be pulling upward so that their sum perfectly balances the weight that is pulling downward. I need to redraw this so that the vectors are proportional. Now, as you can see, when the vectors themselves are drawn to scale, it looks a little bit different than it did with the lengths of the cables, because the cable that is at a greater angle from the horizontal must actually balance more of the weight of the object. So let's move these a little bit more. Let's move them down, because what we want to find out is, oops, didn't mean to leave that there. What we need to find out is how these two vectors that we've been working with that are along the cables balance this weight. So we want their sum to be in the opposite direction with the same magnitude as that weight. So let's put the vector, the sum of the two cable vectors in place. There. That's what their sum should be to balance that red vector down there. And let's get rid of the red one. Okay, because that's what we want to work with. All right, now I need to give you some information. First off, I'm going to simplify things for you and bring a coordinate axis right at the place where those two vectors have their tails. I'm going to tell you that the yellow vector is acting at an angle of 30 degrees, that's a standard angle, with a force of 137 pounds. I'm leaving off the units so my diagram does not get cluttered. While the blue vector has a magnitude of 159 pounds and a standard angle of 138 degrees. However, I do not want to break these vectors into their components and add them. I want to apply the law of cosines. Let me show you how. Alright, I have already moved my blue vector. Let's move the coordinate axis, and now you can see the standard angle of that blue vector is still 138 degrees. But that's not, I don't want to add these still. I want to use the law of cosine somehow. Do I have what I need? Well, I have the magnitude of the blue vector. I have the magnitude of the yellow vector. Those form two sides of the triangle. All I need now is the angle between those two sides. If we look at the standard angle of the yellow vector, it's a 30-degree standard angle, but look at this. This is where we had the coordinate axis originally. And that is parallel to where it is now. We have parallel lines cut by a transversal, alternate interior angles are congruent, so that is 30 degrees. And 138 degrees around to 159, if you went 42 degrees more, you would be back at the x-axis. So now we have 30 degrees plus 42 degrees, or this angle becomes 72 degrees. And now we have a side, an angle, and a side. We can use the law of cosines to find the magnitude and the direction, because we can find this angle here, and then we can find this angle, and we will find the standard angle for that vector, which should balance the weight. Therefore, it should be straight up. It should be 90 degrees right here. But I will leave that exercise to you if you so desire, and you can look for my next video in this series on the law of cosines.